me and all of you for tuning in at whatever time it is, wherever you are. So the Nabla Y operator is a generalization of the Nabla operator. Now we heard a lot of new things about the McDonald polynomial last talk. Try and do better there. Oop. And it has a lot of really interesting analytic properties and a growing body of geometric and algebraic properties. And it's also got a lot of neat combinatorial properties, like shear positivity. We don't understand that yet. We do know basically a nice formula for the monomial expansion. Just some overall words. X to the W fill the shape of mu, and then you have certain Q and T statistics, which I won't talk about in detail, but there's a lot of neat open questions about that. But one of the reasons these things are so important is, well, for one thing, you can obtain almost all the other families of symmetric functions that people have studied, like Schur functions and Jack symmetric functions and Hall-Littlewood's as special cases or limiting cases. But also there's a really nice geometric interpretation in terms of the Hilbert scheme that Mark Heyman found. And that's led to a lot of character formulas for different varieties and SN modules, which are expressed in terms of these McDonald polynomials. And kind of the canonical example is a famous theorem of Mark Heyman. This is Nabla of En, nth elementary symmetric function. Here is the graded Frobenius characteristic of the diagonal covariant algebra DRN, which is what? So this capital Xn is a set of n x variables, and then you have capital Yn, set of n y variables, and then you mod out by the ideal generated by that same thing, but just a positive degree, and which are fixed by the symmetric group, invariant under this diagonal action. Whoa, come back. What the heck? So what do I mean by the graded Frobenius characteristic? I'll just, oh, there's a delay. Hello. There's a delay. Oh, no. So what do I mean by the graded Frobenius characteristic? I'll just describe it in words. So the character of an SN module, of course, here is a symmetric, well, you can think of the Frobenius characteristic as a symmetric function where the coefficient of a Schur function S lambda is the number of copies of the irreducible SN module corresponding to lambda that occurs when you decompose your SN module into irreducibles. And this graded, in this case, there's a bi-grading by homogeneous X and Y degree in this SN module. And if you just take that into account, then you get this graded Frobenius characteristic. So it's a sum of Schur functions with coefficients which are non-negative powers Q and T, polynomials in Q and T. Okay. Now, this Nabla operator, Nabla H mu twiddle, is T to the n of mu, Q to the n of mu conjugate, H mu twiddle. And here n of mu with summation over I. This is a statistic that occurs a lot in symmetric function theory. And by the way, feel free to interrupt at any time with the question. Happy to answer anything. UI conjugate choose to. It's another way to write it. Okay. And I might mention that this is also the scalar product of h mu twiddle with the Schur function as 1 to the n times h mu twiddle. Okay. That TQ power happens to be this. Okay, now, what kind of formula does this actually give you? Nabla En. How do you actually compute En? Well, you have to write En in terms of these modified McDonald's. And there's a identity going back to McDonald, which allows you to do that. Okay, and I think it'd be worthwhile to go through what that is. So these h mu twiddles depend on Q and T. I'll just leave those off to save a little time. So this W mu is a function which arises all the time in this area. So you take the product over all cells of mu. And A and L mean arm and leg lengths. So I draw my partitions in so-called French notation, where square S here, there's going to be four quantities that we'll be referring to. There's the leg, which is the number of squares to the above border. There's the co-leg, the number going down, arm, the number going to the right, and the co-arm, the number going to the left. So this identity here, McDonald, gives you En of xy over m. Oh, I have to explain what that is. So this is a plathistic identity. Now pk of xy over, so m is this quantity that arose a lot in Anna's talk. Okay, 1 minus q, 1 minus t. And pk of these square brackets indicate plathistic substitution. The plathistic substitution of xy over m into pk is defined as pk of x, and pk is the kth power sum. So basically what you do to plathistically substitute something into pk is replace all parameters and variables by their kth powers. So in this m, I replace the q and the t by their kth powers. But I did not replace the negative by its kth power. So you don't replace any non-parameters by their kth powers. All right. And then to define En of xy over m, you'd write En as a polynomial in the pk's. And there's a standard way to do that, which most of you probably know. And then you replace each pk by this in that expression for En. Okay, so that's the definition there. And how do we go from that to a formula for En of x? What we have to do is let y equal capital M up here, because then the m's will cancel, which is a property of Plethism. And then just let the En of x. Okay, so En of x is summation over mu, h mu twiddle of x. And now h mu twiddle capital M, and now we have to use lothistic brackets. So I'll put the q and the t back in there, divided by this w mu. Okay. And then finally, you use one of the basic building blocks of the whole lothistic symmetric function identity world, which is called Hornwinder-McDonald reciprocity. And here's one way to write it. Okay. And B mu is the sum overall S and mu of Q to the A prime, T to the L prime. So for example, how about B 2, 2? So you would draw your shape 2, 2. And if you start with this square here, A prime and L prime are the distances to the left and down. They're 0, so you get 1. And if you go up 1, the co-leg then becomes 1. If you go to the right 1, the co-arm becomes 1. Okay, anyway, that's what this says. This kind of fundamental identity of McDonald's. And then you note that there's a 1 minus z in the denominator on both sides, corresponding to this corner square where the co-arm and the co-leg are both 0. So you cancel those, and then let z equal 1. And then on the left, we get basically what we're trying to find. Oh, excuse me. We get h mu twiddle of 1 plus b. Oh, this isn't going to work. I forgot an important part of the identity. B lambda times capital M minus 1. And so what's left here is something that'll come up later in the talk. So I'll give it a specific name, pi mu, which is the product over all non-corner squares. So that's that. And then on the right, we get the corresponding thing in B mu. Lambda. And then finally, we let lambda equal the partition with the single square. So B lambda just becomes 1. And on the left, now we get h mu twiddle of m. I'll bring this pi mu over to the right, and this pi lambda just becomes 1, and h lambda, so h of a single square is just E1, and this becomes B mu M. Okay. So all that showed that En of x is a summation over mu twiddle of x times m pi mu b mu over w mu. So then to apply Nabla En, you would hit both sides with Nabla, and that would just multiply that guy by this power of q and t that we saw earlier. And you get a big rational function sum in the h's. And we do now have a nice proof that this equals a certain expansion into monomials called the shuffle theorem. We're still hoping to find an expansion directly into Schur's, which we understand combinatorially. But it tends to be really hard to work with this because it is a sum of rational functions. Let's see where I am here, my plan. Okay, so now I want to go on to the definition of a more general operator, Nabla y. It's a linear operator, just like Nabla, and on a McDonald polynomial in x, so here y is a set of variables, and it just multiplies the McDonald in x by the McDonald in y. And note that if I then take the scalar product of that thing there, with, say, s1 to the n of y, then I can use the fact that the scalar product of the McDonald and y with s1 to the n is that power of t and q defining Nabla. So this just becomes Nabla h mu twiddle of x. Okay, so that's why these Nabla y operators contain Nabla as a special case, and might then ask, well, what kind of properties do they have? Well, here's one conjecture, which is kind of the main thing that's been motivating us, is Nabla y En of x. If I take the scalar product of that with some Schur function in either x or y, get fancy and use the copy. Okay. So that's a conjecture.
Is it
And yes.
is it a symmetric function in y? Is it a scalar or?
Yes, so you're multiplying the symmetric function x by a symmetric function in y because it's a McDonald polynomial. So you can just think everything's going to be symmetric. A sum of, like, a basis here would be all possible products of the form s lambda of y as beta of x over all possible lambda beta. And the coefficients will be some polynomials or rational functions in q and t.
Okay.
But what this says is that conjecturally you're actually getting polynomials which are positive.
So in your conjecture, if I pair Nabla y, e, and x with s and x, I get something involving y though. So it's like sure positive and y. That's the,
Maybe I should just write it as
like is
Nabla
sure
y.
positive. And, yeah.
Yes, yeah. Nabla y e n of x, coefficient s beta of y, s gamma of x is in n bracket qt.
Okay.
I've never really worked with these bisets of variables, so I'm not quite sure myself of that notation. Okay. And also you can iterate this. So more general thing is you can have k sets of variables, say, applied to en of x. And then it's going to be sure positive in all sets of variables. And we've done calculations in Maple and Sage seemingly verify this. And throw in another thing here, just keeping the last talk in mind, Francois, who's done a lot of programming with Sage, a lot of work with the elliptical algebra things, he's tested that if you can take Nabla y applied to some g of x from the elliptical algebra. I can't remember something like this, elliptical algebra. So any of those things that are arising from Nabla, the lower Warrington things, or all those things inside convex, concave polytopes. So there's some conjectures there, I believe. So anyway, you just take any of those guys, which are sure positive, you hit it with Nabla y, you seem to still get sure positive things. So what is the motivation for looking at this to begin with? So we saw that it does generalize Nabla, but it does a little bit more than that. It generalizes the delta prime operators, which arise in the delta conjecture. So I'm going to now talk about the delta conjecture, most of which is now a theorem, but not all. Drawing here. Okay, so given a parking function, or the Dick path for, in this case, an 7x7 grid, and you fill the north steps to the right of the north steps with the numbers 1 through 7. So you're strictly decreasing down every column. That's one way to represent a parking function. And I need to describe various data. So AI is the number of area squares which are strictly to the left of the main diagonal. I guess Jing-Su had these paths kind of turned around, and this main diagonal becomes the x-axis. Okay, but anyway, so AI here, there's one square there that square there containing the 5. So that would have area 1. And these others are 1, 1, 1, 0. If you add all that up, 4, you get the area. And then DI, we need to introduce what we call a diagonal inversion. And there's 2 kinds of things there. So a big number on the same diagonal above right of a smaller number, that's a diagonal inversion. Or you can have a big number, one diagonal to the left of a smaller number and below it. So, and then DI equal number of these diagonal inversions involving car in row I and cars above it in rows above it. So the top car, ooh. Oh, here. Things are a little too sensitive, I think. What's this? It didn't even send me to the right. Oh, here we go. Sorry. So what is the DI here? So the 6 and 1 do not form an inversion of either type here. So that also has a DI 0. But the 5 is an inversion with the 1. And the 1 is in a row above it, is not an inversion with the 6. And the 3 is also an inversion with the 1, but also with the 5. So that DI is 2. And the 7 is an inversion with both the 6 and the 1. And the 4 is an inversion with the 1, the 5, and the 7. And the 2 is an inversion with the 6. So any questions about the DIs? But if you didn't catch that, it's not that important. Just there's some simple way to calculate that. And you add all those up, and for 9, we call that dim. Okay, so and then we start with something like this. And then we mark called certain valleys. So a movable valley is a car where if you pushed it 1 column to the left, you would still have a parking function. So for example, that 6 there, I can push to the left and would just go here, and I have a parking function. But I couldn't push the 1 to the left because then I'd violate the decrease down columns. And so in this diagram, the 7, the 5, and the 6 are all movable valleys. And I'm going to mark a certain number of them, in this case 2. And the one we'll call the valley version of the delta conjecture says if you sum over all parking functions and you also weight by what we call a Gessel fundamental quasi-symmetric function to get a symmetric function, but anyway, that will give you a certain symmetric function, which I'll describe. Okay, that's the one kind of part of it. And then there's another part where you have a different, so summation over all parking functions, valley version. Parking functions, and corresponding to past pi, and we'll take t of the area, q to the dim, and then we have a certain kind of suppress a bit of that discussion just for sake of brevity. And we then have this thing here, and we're going to take the coefficient of z to the k. And that's going to be one combinatorial side of the delta conjecture. And another one, we have a slightly different here's a different parking function. And in this guy, I'm going to mark what are called double rises. So a rise is a pair of consecutive north steps in the path. So like this topmost star here is the top part of actually a triple rise. But I'm just going to, for each double rise, I'm going to either possibly mark the top of the rise. So here, the 1 and the 3 would form a double rise. And then I take summation over PF and all pass pi, Q to the dim, T to the area, F is of sigma inverse, and then a product 1 plus Z over T to the A sub I plus 1. So say that now. And this is the bottom of the, maybe I'll phrase it this way. A sub I. Okay. So A sub I being the row, the value of the AI statistic, the number of squares in the marked row. And then you take the coefficient Z to the K in this. And you can think of when you select a Z in this product that corresponds to marking the corresponding row, and you're really kind of removing that contribution to the area. So we call this the rise version. And the delta conjecture says that the valley version, that symmetric function there, which isn't obviously a symmetric function, but you can show it to some of these LLT polynomials. Oh, wait, sorry, let's go back. This we can prove easily as a symmetric function. This up here, this valley thing, it's still unknown if it is a symmetric function. But the delta conjecture says these are both equal and they're both equal to a certain symmetric function applied to En of x. Now, what is this delta prime? So first of all, delta sub f applied to some modified McDonald is f statistically valued. You plug in that b mu alpha bit, which we calculated a little bit earlier, and delta prime f for any f, you don't plug in the 1 corresponding to the corner square. Okay. And it's a fact that if you take the scalar product of McDonald polynomial, say an x, with the Hook-Schur function, that's actually equal to this delta prime E n minus k minus 1 applied to, no, otherwise, so this is equal to E n minus k minus 1 in B mu minus. And the upshot of this is that if you take Nabla y applied to En of x, and you take the scalar product with a Hookshire function, say in the y's, that will be the same as doing delta prime E n minus k minus 1 applied to En of x. So what we're hoping to do is to find a combinatorial formula model for delta y. So open problem. Or more generally for not delta, Nabla y, Nabla y1, Nabla y2, Nabla yk, En of x. And if you did have such a combinatorial model, presumably then it would contain the delta conjecture. You could recover the delta conjecture as a special case. Now, I didn't quite describe what's known about this conjecture. So it's known that these two things are equal. And there's two proofs, one by Diodario and Mellet, and that builds on the Carlson-Mellet method for proving their first proof of the shuffle theorem. And then the other proof is due to Blasiak, Heyman, Morse, Anna, and Seelinger. And that's one of the really nice applications they've had of the catenaminals and all their elliptical truncations. But neither of those have proved this Valley version, and it's really surprising that no one's been able to prove these two very direct kind of combinatorial functions are equal. Okay, and another major goal behind studying this Nabla y is the following. So now and this is a problem that's been open kind of from the start of Heyman's work. For delta E lambda En of x. In fact, ideally, we'd like, so this is for any lambda. Or more or less equivalently for this. And we'd really like to find delta S lambda of En of x, a nice model for that, but that might be too tough. It would be really nice to have this delta E lambda, and note that if you had Nabla y1, Nabla y2, Nabla yk, en of x. And you took the scalar product of s okay. So let's see, I want 1 to the lambda 1, I think. So whatever a Hookshire function, so that's n minus lambda 1, comma, in y1. And so what you can do, because these things are all independent, you could take a given appropriate Hookshire function from each yi to get the delta prime of e lambda. So this, which equals delta prime e lambda 1, delta prime e lambda 2, just by definition, more or less. And if you had a model for this, by specializing it in the right way, you would get a model for that. So that's the point there. So let me check where we are. Okay. So what can we prove so far? What we can do is prove we have a combinatorial model when one of the parameters is equal to 1. And it's a model for this more general thing here. So we kind of know what the objects are. They're kind of generalized parking functions. And we're just searching for a way to generalize the dim statistic. We have the area. And I'm going to give an example of this object here. So I've drawn each north step and each east step as like twice as long as normal, just so I can fit in what I'm going to do. Because instead of a parking function, now we have a bunch of ordered pairs instead of just single cars. Okay, so there's an example of the objects when we're just looking at Nabla y, en of x, evaluated at t equal 1. So we're going to take q to the area of such an object. And then we have a term involving the x's. And this is going to be, what you do is you form the reading word. So what is the reading word? read the long diagonals outside in. So I'm gonna put so the farthest out term is that guy. I'll put the first coordinate will be like the X, and I'll put that above the Y for what I'm going to do next. And then the next term, I guess, is the 3. Now we're reading along this diagonal. And 4, 3, 2, 8. And then finally along the final diagonal, 3, 2, and 1, 1. So for your Gessel fundamental, for those of you who know what that is, you need an inverse descent set. Oh, so wait, sorry. For the X's, I'm just going to use the normal X weight. So there's 2 1s in that top sequence. And then for the Y's, I'm going to take the inverse descent set of that permutation. So 2, 3, 4, 5, 6, and 1. Anyway, you sum over all these objects, and what is the exact condition? So in each column, you have to have strict decrease along each coordinate. So that's kind of like a parking function in each coordinate. But there's another condition that if you're exactly 1 away, like here, so if you have a east-north, you have 2 squares which are right next to it on the same diagonal, you have to have strict decrease in at least one of these. This is kind of a new condition that comes in. So here we have a 4 bigger than 2. So that is a strict decrease there, and that makes that a legal thing. And up here, the 3 and the 1, and the 6, and also you have 2. Okay, so this is the kind of object we have. And if you have more than one set of variables, for example, say you had a y1 and a y2 set, then you would sum over paths in an n by 2n rectangle. And then you would have triples. You need to stay above the diagonal here, just like in the rational combinatorics world. Then you have paths here, and then you have triples. And then between any 2 successive north steps, you have to have at least as many east steps as you have non-descents when you look at coordinate to coordinate matching. So that's an example of this is here. Because we have 1 non-descent, namely the 3, 8, then we have to have at least 1 east step between those successive north steps. Okay, so anyway, there's a nice extension to general sets of variables. And I've chosen this guy here because it illustrates a connection with the Valley version of the delta conjecture. So you can, this reading word here in the Y's was a shuffle of 2 big cars in increasing order and the rest small cars in decreasing order. And you can think of these big cars, in this case the 78, as corresponding to marked. If you go right above the square using those cars, you'll have a valley if you removed the Y things. So if I remove the y's, which are these guys here, and leave the x's, I didn't erase here. Then I have two marked movable valleys. And that's how this unknown statistic, which I guess is like T of the dim question mark, if our second set of variables is one of these so-called hook shuffles, then we can use the valley version, the statistic from the valley version, where you take these DIs and subtract off certain rows. We can use that to correctly generate what we want. And then basically, let me just finish by saying that the proof of this T equals 1 case is mainly due to Marino. Well, it's all due to Marino and Alessandro. And it's like a 20-page proof, and it uses a lot of stuff, bijective things that Marino used to prove that T equal 1 of the original delta conjecture. He has a paper in Transactions doing that, a fairly involved combinatorial thing. And then he and Alessandro have a paper, recent paper, where they study theta operators, which I don't have time to get into, but that's like a more advanced operator, which has come along to solve a lot of open questions in pathistic McDonald world, and was behind one of the proofs of the delta conjecture, the rise version. But anyway, Marino and Alessandro really went to town. When you have all these Nabla operators, it seems to be kind of a natural generality where Marino's method applies. So they have all these intricate bijections combined with complicated application of theta operator identities to finally prove this theorem. And I'm going to stop right there. Thank you.
Is there any question or comment? Yeah, Brendan.
Right. Well, great talk. Thanks. Do you have any
Right.
idea what happens at T equal 1 over Q?
Mm-hmm.
No, that's a good. Oh wait, I'll take that back. What did we do? In the delta conjecture at T equal 1 over Q, something good happens, as I recall.
That's right.
Yeah, but I don't recall ever actually even looking at the T equal 1 over Q case of the Nabla Y. I think I have a vague memory that Francois did that, and there's something good there.
Okay.
I wish I had a better answer for that.
And is there any hope for like a module theoretic interpretation of this?
So I haven't. Let's see. So of course there's Zabraki's conjecture for the module corresponding to delta, which I know you are well familiar with, and this would have to be something a lot more than that, right? Because you have to have the whole McDonald polynomial somehow. It's just the coefficient of the given hook sure is giving you that. It was giving you Zabraki.
Or you need like an SN cross SN module because you have two sets of variables, or in general, it would be like a K+1 full product of SNs. And, you can kind of see that action on your sort of generalized parking functions, but.
That could really be a nice thing to look at, I guess.
Okay, cool.
Yeah. that's wide open for sure.
And I have a few questions.
Yeah.
Is your formula for t equals to 1 is it gives your positive formula or just F expansion?
Oh, so one version of it is an expansion into e's.
Oh, okay.
So, but not in the y's, in the x variables.
Oh,
Yeah, there's like two versions of this main theorem. One, you have an e expansion in the x's and monomials in the y's, and the other one you can kind of collapse the x's to nothing and kind of add in that, and anyway, you just have monomials in the y's and the x's.
okay.
Okay, but there's no Schur model. Of course, if we had a combinatorial Schur model, then we would have one for Nabla En.
Mhm.
Yeah.
And what about the t equals to 0 case? Have you ever thought
Right.
about
I remember what we know about that. Oh, so even when t is like when q is 0, so there's no area, this problem finding the div
Oh,
is unsolved.
oh, okay, okay.
Yeah, so it seems to be some tricky thing. We haven't been able to figure it out.
Okay. Thank you. Is there any question or comment?
I have a question.
It's- so-
In the delta conjecture, what makes the value version so hard to prove?
Right. So I wish I knew more, but one of the things that makes it hard to prove is that it's not obviously a sum of LT polynomials. So if you think of the rise version here, okay, so if you fix a Dick path of pi,
Mhm.
and if you ignore this thing here, then that, the area comes out and the sum q to the div after that is a LT polynomial. Now, what happens if you take away some of these? Well, you're not changing the path. You're just taking away some of the areas. So you're still getting an LT polynomial. All you're doing is changing the area. But in the valley version, when you start to remove these DIs, you're not only are you not getting an LT polynomial anymore, you're not getting anything that we recognize as a symmetric function. And Andy Wilson has studied this, and he's come up with a really neat potential generalized LT polynomial, but he can't prove it's symmetric, let alone Schur positive.
Thanks a lot.
So, but anyway, this is really surprising that we can't even. This is like 7 years after the introduction of this conjecture, we still can't prove that this combinatorial thing is that. It's a little embarrassing, actually. But this area is full of embarrassing problems.
If there's no more question or comments, thank you all for participating in various time zones, and hope we can see you all again tomorrow. And if you have any question, please let us know through email. And there's lunch boxes outside of room 220 for those who are participating in person in SNU. And that's all. Yeah. See you guys tomorrow. Bye.
Thanks. Yeah.